In the previous video lesson, we used Coulomb's law and the law of superposition in order to find the net amount of electrostatic force on this 6 microcoulomb charge, assuming that all 4 charges that you see here are fixed in space. And as a quick reminder, the way we did this, we pictured it like a free body diagram. There's a force of repulsion between the 5 microcoulomb and the 6 microcoulomb. There's a force of repulsion between the 4 microcoulomb and the 6 microcoulomb. And there's a force of attraction between the -3 microcoulomb and the 6 microcoulomb. We had to do some vector math to break the one vector that's pointing at an angle into its components, and then we recombined all the vector components using the parallelogram method. Okay, so what we ended up with was the net force as a vector quantity was equal to the force between, I think we called these charges 1, 2, 3, and 4. So the force between charge 1 and charge 4, plus the vector force between charge 2 and charge 4, plus the vector force between charge 3 and charge number 4. If we write that out, applying Coulomb's law, we get K Q1 Q4 over R14 quantity squared plus K Q2 Q4 over R24 quantity squared plus K Q3 Q4 over R34 quantity squared. Now if I really want to be correct, this is a vector summation, so there's going to be some R hat on all of these. Anyway, the one quantity that every one of these terms has in common, well, there's a couple of them, they all have a K, but they all have this Q number 4, right? So we could factor that out. We could say the net force is equal to charge number 4 times the vector sum of KQ1 over R1 squared plus KQ2 over R2 squared plus KQ3 over R3 squared. I've changed my notation a little bit here. I guess I can keep this R14, R24, R34. Okay, so question is, what would each one of these terms be? For one thing, what units would each one of these be measured in? If this Q4 had not been factored out of it, these would be newtons. But because we've factored out one of the charges, that means these are all newtons per coulomb, right? So we're going to take a summation of newtons per coulomb and then multiply that times some number of coulombs. And so in the end, we'll have an overall value in newtons. What we're really doing then was we're saying the net force on charge number 4 is equal to the charge of charge number 4 times this overall quantity expressed in newtons per coulomb. That overall quantity is known as the electric field, okay? So if I multiply the net electric field times the charge, I get the net force on that charge. This is very similar to finding the net force gravitationally. If we had one planet and one satellite, and we had to find the force on the satellite, then we're just going to use Newton's law of universal gravitation. If we call the planet capital M and the satellite lowercase m, then the gravitational force is Gmm over r squared. But what if we had a planet and a moon and this satellite, and we wanted to find the net amount of force? We could apply Newton's law twice. We could say capital M number 1 and capital M number 2 and lowercase m, and we can find a force between these two. We can find a force between these two. In the end, what exists at this location in space is some particular net gravitational field strength. And if I want to find the force on this mass, all I need to do is multiply that mass times whatever the local net gravitational field strength is. Okay, so when you see this equation, F equals QE, or when applying the superposition principle, net force equals Q net electric field, think of that in terms of an equation you're already familiar with. That is either F equals mg or net force equals m times net g when we have to apply superposition principle. So this is it. Just as gravitational field is a vector quantity with units of newtons per kilogram, electric field is a vector quantity with units of newtons per Coulomb. Now the value of it, if you recall, you might need to review the previous video lesson, but I think we found that this force was somewhere around 250 newtons. If I remember right, this was like 180 newtons, and this was, anyway, that's beyond the point. Let's say I changed my mind and decided I don't want to solve, I had my numbers wrong, I didn't want to find the force on a 6 microcoulomb charge sitting in this position. This was supposed to be a 7 microcoulomb charge. Regardless of what that charge is, whether this charge number 4 is here to experience the force or not, even when I take that charge away, at this point in space, there's a force waiting to happen, right? If I were to put some charge Q here at point P, these 3 other charges are just waiting to exert some net amount of force. So we say at this point, there's a net electric field even when this charge isn't here. Now, once I bring the charge here, then there's not just an electric field, there's actually a net electric force that I could find by multiplying this charge Q by whatever the electric field is at that position. So regardless of what value I choose for this charge, it could be any value, the electric field at that point isn't going to change as I change the amount of charge I put in this location. So for example, let's just find the electric field at this point. Let's find the part of it strictly due to the 4 microcoulomb charge. So electric field can really be defined as force per unit charge. And as we know from Coulomb's law, force is found by pairing up any 2 charges, Q1, Q2, over R squared. So electric field is KQ over R squared. Electric force is KQ1, Q2 over R squared. In other words, it takes 2 charges at minimum for there to be force, but any one charge all by itself has the ability to create an electric field. All right? If I want this to be a vector statement, then I can put the vector symbol over the E and include an R hat in the end of the equation. But we're just going to concern ourselves once again with magnitudes, and we'll show the field as a vector quantity in a diagram. So if I get rid of the charge here, at this point in space, there are 3 electric field components. There's an electric field pointing this way due to the negative 3 microcoulomb charge, right? So think of the electric field as a force that's waiting to happen, but it doesn't exist until a charge Q is placed at the point in question. Okay, so this is not a force, it's an electric field vector. And it's the electric field due to the 3 microcoulomb charge. There's another part of the electric field due to the 4 microcoulomb charge. And there's yet another electric field line, or electric field vector, I should say, due to the 5 microcoulomb charge. And this is 37 degrees, and I can find the value of each of these individually. So the electric field due to the 5 microcoulomb charge at the point P, which is a distance of 4 centimeters away, is equal to K times the charge of the distance from the 5 microcoulomb charge to the point in question is 5 centimeters, Anyway, KQ over R squared. 9 times 10 to the 9th Newton meter squared per Coulomb squared times 5 times 10 to the negative 6 coulombs divided by 0.05 meters quantity squared. Okay, so the meters get squared and they cancel out. One of the coulombs cancels, but not both. So our overall answer is going to be some number of newtons per coulomb, which is exactly how we measure electric field strength. If you grab a calculator and multiply 9 times 10 to the 9th by 5 times 10 to the negative 6th and divide by 0.05 quantity squared, you get a rather large number, right? I believe we get 1.8 times 10 to the 7th newtons per coulomb. The electric field due to the 4 microcoulomb charge is 9 times 10 to the 9th times 4 times 10 to the negative 6th divided by, okay, yeah, in this case the distance is 4 centimeters, 0.04 squared. Okay, so 9 times 10 to the 9th times 4 times 10 to the negative 6th This gives us 2.25 times 10 to the 7th newtons per coulomb. And if I want to find the electric field due to the 3 microcoulomb charge, 9 times 10 to the 9th times 3 times 10 to the negative 6th divided by 0.03 squared. And again, you might say, wait a minute, shouldn't that be negative? Well, yes, it is a negative charge, but again, I've already dealt with the fact that it's negative by drawing this electric field as a downward pointing vector. And all I'm really interested in right now is magnitude, right? So I can keep all of my charges as positive values in my computation. Okay, so this time we get three times 10 to the 7th newtons per coulomb. Okay, so again, if we draw this as a vector, we have 2.25 times 10 to the 7th, 3 times 10 to the 7th, and 1.8 times 10 to the 7th at an angle of 37 degrees. So we try to make this a resolved vector diagram. It's not a, this isn't technically a free body diagram because free body diagrams are only for force vectors. So it's a vector diagram, but not a free body diagram. It's an electric field vector diagram. We resolve it. We can leave these alone, call this 2.253. We know in the end we're going to multiply everything times 10 to the 7th newtons per coulomb. So I can simplify and just look at the numbers that come before the 10 to the 7th newtons per coulomb. Okay, so this is going to be 3/5 of 1.8, and this is going to be 4/5 of 1.8. Or in other words, 1.08 and 1.44. So I add 1.44 plus 2.25, and I get an overall vector to the right of 3.69. I subtract 1.08 from 3, and I get a downward vector of 1.92. So I use the parallelogram method. I find the net electric field vector in magnitude is equal to the square root of 3.69 squared plus 1.92 squared and And so we get about 4.16 times 10 to the 7th newtons per Coulomb. Now remember, in the previous lesson, we tried to figure out what's the force when at this point P, we placed a 6 microcoulomb charge. So if I want to find the force on a 6 microcoulomb charge, I multiply that amount of charge times the electric field at that point. Or in other words, the net force I'm finding on that 6 microcoulomb charge is 6 microcoulombs times this net electric field. So the net force is 6 times 10 to the negative 6th coulombs multiplied by 4.16 times 10 to the 7th newtons per coulomb. Coulombs cancel out. And we get the exact same answer we got in the previous lesson of 250 newtons. But the power of solving it this way is I can say, wait a minute, what if it wasn't a 6 microcoulomb charge here? What if I put a 7 microcoulomb charge? What if I put an 11 microcoulomb charge? You could put any amount of charge there. Now that we've already found this, the final step of finding the force is easy. I can take any charge I want, and the net force on that charge is going to be its value multiplied by 4.16 times 10 to the 7th newtons per coulomb. So this is the idea of the electric field. Force is a quantity measured in newtons and requires at minimum 2 charges for there to be force. Electric field is also a vector quantity measured in newtons per coulomb, but it doesn't require 2. It just any single charge creates an electric field, right? Coulomb's law says as long as I have 2 charges and I know the distance between them, I can find the electric force between the 2 of them. There's Q1, there's Q number 2, and the distance between them is R. If I just had the same charge Q1, and I don't have a second charge, I just have a point in space at that same distance of R, then I know what the electric field is at this point. Even with there only being 1 charge, there's still an electric field, and that electric field is K times the 1 charge divided by distance squared. So the electric field at this point would be something different because it would be a different R value. So at every unique point in space, there's a unique value of electric field, but we can find it using this formula. Okay, thanks for watching.